morning, good afternoon, good evening, everyone. Welcome to ICANN X Talks, Connecting the World and the Universe. I am your host today, Professor Martin Thuo, coming to you from North Carolina State University in the eastern side of the United States. This month, we continue our series with Professor Nicholas Kotov after last week's talk by Anthony Mikos. And next week, we will continue the nano theme with Professor Raphael. Today, I will be assisted by a panelist of Professor Dixon Andala from the National Research Foundation in Kenya and Multimedia University, Professor Takuya Nakashima from Osaka Metropolitan University, and Dr. Julia Chang from Fudan University. Our speaker today, Professor Nicholas Kotov from University of Michigan, is a Irving Langmuir Distinguished University Professor in Chemical Sciences and Engineering, and the Joseph B. and Florence V. Zieska Professor of Engineering at the same university. Nick is a pioneer in complex nanostructures and their assembly, leading an international team of scientists advancing practical implementation and theoretical foundation of biomimetic nanostructures. Chiral structures represent a focal point in his work. And Nick has many, many awards. I don't think I want to steal his time. He has a ton of them. And more recently, Nick has been elected to the National Academy here in the US. He's a fellow of the AAS. He has led a very productive group, and they have had a few startups. Some of these technologies have transitioned into battery technologies, into automotive industry, among many other things. And besides the fantastic work that Nick is doing, he is also a big advocate for scientists with disability. And I will not steal any more time. So, Nick, I want you to take the floor.
Martin, thank you very much for very kind and too generous introduction. It's a great honor to be a part of this event. And I very much appreciate the possibility to be a part of this conversation. Welcome to Chirality, Complexity, and Graph Theory. So what I would like to do today is to take you for the journey in biomimetic structures. They all at the nanometer scale, and they all will be related to the questions which are connecting chirality and complexity. How do we describe the complex nanometer scale structures? And it turns out that graph theory is very useful here. And how we engineer the complexity and how we make this knowledge quite useful. And I'll give you two examples here. One is in the realm of machine vision, and the other one is in the realm of batteries. So why do we want to make complex structures? Because nature used them a lot. And these are some examples: enamel, bone, and cartilage. And all these materials, or actually systems, are self-assembled. They're made from nanoscale components, particles, and fibers. And they have a distinct non-crystalline order. All that results in the unique combination of mechanical, chemical, and biological properties. And these are not just these materials. We can also see the same non-random patterns and same very unique functionality in many other cases in the biological worlds. For instance, spiky particles are very common. You can see them in viruses, you can see them in algae, you can see them in pollen. And in all of these cases, the reason for their emergence are the colloidal chemical and biological properties and basically the control of interactions. So now the question is how and why these particles evolve this way, and why we want to make and we want to replicate these complex structures. The first entrance into this realm of questions was made quite some time ago by Murray Gell-Mann, who looked at the biological materials and kind of introduced a concept of effective complexity. And in that case, it related to the fact that all the unique and highly functional biological materials have some amount of order and disorder combined, and then their complexity and functionality is at maximum. I'd like to know that these axes are notional. They have no quantities associated with them, and he did not really introduce anything of that sort. He didn't tell us how to do it. With that, we don't know how to place a bone or algae particle or cartilage here. In my past work, we learned that nanoparticles also can self-assemble into these complex structures, and the nanoparticle building blocks are very useful. They're utilized in many areas of technology. And we want to understand this realm of relationships between the functionality and complexity by using the case of nanoparticles. In these assemblies, we actually encounter two problems. One, that the nanoparticles always have some degree of dispersity and therefore some disorder. So we don't know if we are too far, maybe on the right side of that graph. The second part is actually less appreciated, is that all the complex structures are actually related to a maximum or at some high point in the thermodynamic landscape of particle systems. And if we want to look at the minimum, it will always be associated with disorganized high mass states due to the entropic and enthalpic factors. So we need to have some kind of a restriction in the assembly. And that restriction will prevent the system from ending up in that valley of death. So in our past work on layer-by-layer assembly, for instance, with clays or graphene oxide particles, we learned that electrostatics provide very efficient restrictions for the particle assemblies. For example, if we use charged platelets, then we can always form just a monolayer of, for instance, graphene oxide particles or clays. The same can be utilized in many areas of technology, as we know, for instance, for graphene and graphene oxide. In the bulk solutions, we also learned that it's possible. And in collaboration with Sharon Glotzer, we show that electrostatic restrictions between the particles results in the formation of uniformly sized supraparticles. They contain maybe 200, 300 nanoscale particles. And if we want to add more particles there, electrostatic restriction will say, no, I'm at thermodynamic perfect state and I don't want any more particles. So by using these ideas, we started asking question if we can form the complex particles with chiral particles, because in biology, we always see the chirality, and maybe that's one of the important factors. And so we decided to make the chiral particles in the shape of nanosheets. So these are two-dimensional materials, just like graphene oxide, clay, and others. And unlike those, they have a layer of chiral organic ligands on top and on the bottom of these sheets. these are stanates of gold sulfides, and they are definitely very polydispersed. And by partially in our surprise, we saw that they actually form very intricate and very unique type of particles that can be called the chiral hedgehogs. If we have monochiral amino acid on top and on the bottom. So if we use L-cysteine or G-cysteine, the pattern, size, and geometric parameters of these particles are very much identical. If we use a mixture, equal amount of G and L-cysteine, we also form interesting particles. We can call them kayak particles, but they have completely different shape. So, in addition to electrostatic restrictions, which are certainly present here, we see also some other restrictions, say the hydrogen bonding restrictions or elasticity of the nanosheets. If we use L and D amino acids as a start, we see a big difference in the geometric organization of the spikes. They twist and fan left or right, depending whether these are L or D amino acids. And the electrostatic restrictions are very powerful, and they result in this amazing uniformity of the chiral hedgehogs, regardless if it's L or D, and they can be made in vats. If we change slightly the conditions, say the temperature of the reaction as well as the concentration of L and D amino acid as a start, we now can produce a very wide range of the particles. And we can make supraparticles or twisted bundles or star-like particles or supraparticles from supraparticles. Now the logical question is, which particle is actually more complex? And this is not an easy question. And I actually spent about a year, during the pandemic time, pondering about it. And the best answer to that at this moment is the application of the graph theory. Because in the realm of graphs, and these are the part of the discrete mathematics, these are sets of nodes and edges, and the edges interconnect the nodes. So in many cases, the complexity is the built-in information in these graphs. And there are many parameters that we can use to quantify the complexity. It could be, for instance, the multifractality or connectivity index. We use the previous studies by Zrandic and Plavich on complexity index in the organic chemistry, and we extended it to semi-infinite nanometer scale structures and adapted it to the nanoscale organization. It's actually not too hard, and it's actually applicable to all the nanometer scale assemblies and structures. For instance, to the nanoparticle chains that you saw, or to the nanorods assembled, or to the snake-like structures that are made from a variety of two-dimensional materials, to superparticles and superlattices. What it is in the essence is that if we have a random shape or spherical, or for instance, in some cases, cubic particles, we denote it as a node, or actually K1. If the particles are interconnected by a different material, and quite often this is an organic material, that will be described as an edge. And this can lead to a number of very easy representations. For instance, extension of that logic would be the minimal representation for the more complex building blocks. Unlike atoms, the nanoparticles can have a variety of nanometer scale shapes. If this is rod, it will be K2 graph. If it is a sheet, it will be K3. If it is a chiral nanometer scale structures, it has to be represented as a minimal representation by K5 graph, because it's out of plane structures, and this is the first out of plane. So now let's apply the same rules. And if, say, rods are interconnected, this will be the edge. If sheets are interconnected, this will be the edge. So now with that idea, let's try to check if our understanding of complexity is adequate, and if the numbers that are given by the graph theory relates very well to our intuitive vision of complexity in the nanoscale structures. So if we calculate the complexity index by using this simple formula, we get, for say, a pair of particles, complexity index is 1.5. If it is chiral, so it is twisted, this is the minimal representation, then the complexity index rises very fast. For instance, chains, which are very common, we can have immediately the value of complexity index 6, which is actually makes a lot of sense, because this is the one-dimensional crystal, and the pattern here is very easy. So it's more complex than one particle, more complex when a pair of particles, but it's less complex than a three-dimensional carbon structure. So now we have a tool, and we can apply it to a variety of the materials that can be self-assembled from inorganic building blocks. For instance, supraparticle from nanosheet will be represented by this graph. So this is the sheet. It's this loop represents the boundary conditions, and they're randomly placed inside. If we have the nacre-like structures, this is not random, and we have the stack of the planar particles, and they're interconnected by the organic layer, and therefore we have this graph representation. And we can calculate now the complexity index. It is 6 for the supraparticles, and it will be 24 for the nacre. So, and now you can already may see the emerging point here that the higher the complexity index, the higher the functionality. And indeed, you can, if you look around you, there are nacre materials or nacre-like materials in many structures that you see. A lot of co-votings are made in this way. Actually, quite a lot of electronics made in this way, and like. So let's look at the foundational aspects of the complexity and functionality, and let's now calculate the complexity index for these structures. So the kayak particles are made from sheets, they're asymmetric, and these hedgehog particles are made from chiral ribbons. They're also stacked and inside the rough light sheets. We calculated here the complexity index 40 and complexity index 87. There are many optical and catalytic and other properties of the moral hedgehogs, which I would love to talk about, but maybe in a separate opportunity, but this complexity index is very high. And it gave us quite a bit of pause at that time, because if we calculate using identical tools the complexity index of the prototype particles of the vocalith, it's also chiral, these are single sheets, we see that complexity index for the lab-made particles is actually higher. And the big question is, can we actually outdo the complexity of nature? Of course we can, and it's happened all the time. But the true question is when the complexity is enough. So when your functionality and complexity are adequate to what you would like to do. And that leads to engineering and some other interesting questions that you will see in a few slides. So now let's have a look and elaborate a little bit more the graph theory for other structures. And I'd like to make a point here that it's not just the case of very complex chiral particles. There could be very complex achiral particles, and the graph theory enables us to describe them in a very simple mathematical form, which is actually identical to that of the molecular structures based on atoms. And we can calculate the complexity indices here. And for instance, for this, asymmetric particles with spikes, it is indeed high. The most importantly, that now when we have these tools, we can combine them with machine learning and start engineering these particles a priori, and then by using different types of restriction and assembly pathways, we can build these particles at will. So these tools are not only applicable to particles, they're also applicable to other materials, for instance, gels. These are self-assembled gels from lead wellrite particles, and we see very distinct dependence between graph theoretical parameter average nodal connectivity and storage modulus, which is very significant part of the gel application. We can also apply the graph theory to describe the interactions of particles and proteins and design them for perfect fit to each other. And these graphs, they include a number of parameters here, and machine learning can be a part of that. That type of engineering. We can also, and this was done in collaboration with Professor Chuan-Nai Xu from Jiangnan University, design these chiral particles from gold, for instance, to specifically interact with proteins on the surface of the cell membranes, and by tuning the chirality, we can tune the immune response. All these are very kind of immediate and very good examples of applications that we can start using these approaches right now. Still, I would like to return to this part because it's near and dear and it's foundational for next steps. And the big question here on this diagram is how to understand the relationship between chirality and complexity, because it's foundational to how the nature builds us and how we can learn from it in order to build the particles and materials from ex vivo. By using the graphs, we now can map the this phase diagram with the complexity indices. And here is one unexpected finding that you can see here. Yes, if we maximize the chirality, and that is in this case the enantiomeric excess of L-cysteine over GD-cysteine, or in reverse, we maximize the complexity as well. But there are many areas of this phase diagram where complexity is low, for instance, here in supraparticles, but the chirality is high. And so is here, the chirality is zero, but the complexity for kayak particles is fairly high. And this also is confirmed in a simpler case. For instance, for the gradual change of the composition of the viral hedgehogs as we add a chiral component to thioglycolic acid, and we see the complexity changes. Initially, it drops very precipitously to this random agglomerates, then it rises to this asymmetric supraparticle, and then it drops again. So altogether, it means that the question about engineering of complex materials by using the chirality has a number of answers. First of all, the monodispersity of the chiral structures in particular, and actually other structures too, is not required. So we can have very dispersed samples, but due to the electrostatic and other restrictions, we can actually control and prevent the system from entering this this realm of randomized agglomerates. The second part, that chirality is a factor, a big factor of complexity. But what it actually does, it introduces the competition of these restrictions. So electrostatics is competing with other restrictions, for instance, how the chiral structures fit together, the elasticity of the nanosheets, the energy of interactions between the ribbons or between the particles. And so the complexity originates actually not from the individual fact of asymmetry, but rather from the competition that this mirror symmetry engenders. And also one big point here is that chirality is universal because it translates from scale to scale to scale. And by that translation, that it doesn't care about is it big or small, we can engineer the complexity throughout the structure. And I'd like to show you some of the examples of that in this work on supraparticles that are self-assembled, and they're self-assembled from chiral sheets. In this case, I would like to show you that the chirality and complexity are certainly related, but the functionality is more related to complexity than the chirality. And this work is based on a self-assembly of the nanosheets in the stacks, and they are made from cadmium steinate, and we keep the shape constant. And as we discover the structure, it's also very similar to the structure of the spikes in the viral hedgehogs, but in this case, we have the gradual hierarchical buildup of these particles, and the restrictions are consisting here from electrostatic, chiral, and elastic restrictions, and that determines the overall shape of these particles. As we change the competition, we change, for instance, the concentration of cysteine, or we change the concentration of cadmium, we see that we can change gradually the shape of the particles. And we can have them big or small. If we have them twisted or not, we see the formation of a particle of a different geometry. In the same time, due to the electrostatic restriction, they all retain that the size, and they also can be scaled in vats. One of the big findings here, which needs to be pointed out, that due to the fact that now we learn how to engineer the particles, we can engineer their optical properties related to this microscale chirality originating from the nanoscale chirality. And this transfer of asymmetry results in the gradual change of the circular dichroic spectrum. And as we twist more, as the size increasing, we can shift it left and right. And indeed, some of you might remember that it's actually quite similar to what's happening in quantum dots, and it is indeed quite similar. Just the difference is that here we have the electromagnetic resonance not with excitonic states, but rather with the dielectric states of these particles, and these bands, they correspond to a dipolar and quadrupolar resonances. One big finding in this realm is that by using the chirality and assembly, we now can change the width of these particles very gradually, and we can obtain the so-called chirality continuum, which is not possible actually, for instance, in case of amino acids. And we can gradually change the pitch, size, length, and width, and also we can change the chirality index called OPD. Unlike the previous findings, for instance, with helicenes or amino acids, we see a very distinct change in dependence between the chirality index and the optical properties. And by using this, I would like to give you an example how the complex particles can be used to address some of the big questions now, for instance, related to the machine vision. By changing the twist, we can change the reflection and scattering of the particles which are used, for instance, as markers for LiDARs. And the LiDARs are, of course, a part of the machine vision, are very much needed for the robots to navigate, and accuracy of navigation is the one which prevents the greater proliferation of a lot of robotics technologies. These markers can help. The last portion is related how the complex materials can be used and engineered for the specific purpose, and this is related to the complexity of nanofibers. And you saw in the initial slides that cartilage has very intricate but repetitive patterns. And cartilage is amazing material. It serves us for many years, and we abuse it, and it still works. And that network structure made from self-assembled nanometer scale structures is complex. And how to replicate it, and how to engineer the comparable material. We can use the same approach. We can design that by using the graph theory, and in this case, the nanofiber are the K2 graph, just like the nanorods, and the junctions here will be the nodes. And now we have the same tools, and we can extract the graphs, for instance, from a number of these network materials for cartilage or cellulose or assembly of gold particles and others. And we developed a tool called Structural GT software. It's free. And by using these graphs, now we can analyze how the parameters of these assemblies, and these are a number of graph parameters that you can use. They're related to short-range organization or long-range organization of these materials. They can also identify some weak points in the structure. They describe the transport of stress. Could be also electrical properties, could be also mass as well. And for instance, the parameter of eigenvector centrality can very quickly identify where the potential failure is. Now I would like to give you a quick example of how this graph theory can be used to design complex materials. For instance, if we want to replicate cartilage or some other structures, we can do it, and how to adapt its properties to the needs that you have. So first, let's ask the question whether we can identify the structure by using the graph theoretical parameters. We extract them from the scanning microscopy images. We use this set of parameters, and you can see that, for instance, for aramid nanofibers, we have very similar parameters to the actual cartilage. For gold wires, we're not. And this is related to how they self-assemble. Certainly, this is a combination of order and disorder, and these parameters just give you a different description of order. It's different than crystallinity, because it describes how the connectivity of the system helps it serve its function. And we established in the past the relationship between, for instance, Young's modulus of aramid nanofibers and a graph theoretical parameter average clustering coefficient. And it turns out that there are very distinct relationships there. They're originating from the Maxwell isostasticity relationships, and in this way we can design the material with a specific toughness and with the specific models. The application of that is wide, but one case is very clear. These are the applications in energy fields. So I'll give you the example how this combination of properties that are very much seen in biology can be described by the graph theory and can be applied, for instance, for lithium-sulfur batteries. One of the big problems there is these separators or the membranes, which are inserted between lithium anode and sulfur cathode. They have to have multiple functionalities related to transport. They have to be strong. They have to prevent the diffusion of polysulfides, and they have to prevent the growth of the dendrites. So we made these membranes from aramid cartilage-like fibers, and it turns out that immediately we see that this structure of nanometer scale pore can be very effective in prevention of diffusion of polysulfides. And this can be seen in the diffusion in macroscale flask. This is the traditional separator. This is our artificial-like separator, and the time here is much longer. And it also can be seen in performance. For example, these batteries, which are designed for specific toughness, for specific stiffness, they have much smaller GK per cycle as some other batteries. And the cycle life for these lithium sulfur batteries can be as high as 3,500 cycles. It's multiple orders of the magnitude greater than some initial sulfur batteries that have been created. All that is based on understanding how the complexity of the material can be engineered and how we can utilize it further. With that, I'd like to thank wonderful people who I have a great honor to be associated with. My students, my postdocs, you can see them here. And I'd like to thank you for your attention, and I'd like to thank the funding agencies that generously helped me in this research. With that, I'm happy to open the floor for the conversation and answer your tough and very inquisitive questions. Thank you very much.
Thank you very much, Nick. It's a big delight to always see the great work you're doing, and for us to have you and learn about graph theory. It's very interesting because machine learning and AI have become a very critical piece of our lives. And for you highlighting that, we are very, very grateful.
You're absolutely right, Martin. I think when you have the numbers, you can apply the machine learning.
Yes. And one of the things that it's a comment that came from one of the students actually from here in the US is realizing how much math is needed in material design. And I'm like, it's obvious. So you should use mathematics if you want to get speak the language of science. And so with that, I want to open the floor for. Let me share my slides. So I want to introduce our speakers, our panelists, and so to get us started, we have Professor Dixon Andale. Dixon is the CEO of the National Research Fund in Kenya. That is the equivalent of the NSF in the US. And Dixon has many accomplishments. He got his PhD here in Binghamton, New York, and then worked as a postdoc with Kyle Bishop, who is now at Columbia, and then moved back to Kenya, where he has risen through the ranks to an associate professor in organic chemistry at a multimedia university. He's a fellow of the Kenya Academy of Science and the Africa Academy of Science. He's very involved in the African Material Research Society in different capacities. And he has many, many awards that I'm not going to get into, but more importantly and relevant to this work, he has authored some great work in nanoscience. Our next panelist is Professor Takuya Nakashima from Osaka Metropolitan University. He's a professor in the Department of Chemistry and received his PhD from Kyushu University. And then in 2004, joined the Division of Material Science at Nara Institute of Science and Technology, and then moved on to be assistant and then associate professor in his current position. He has also been, interestingly, a visiting professor at Michigan. And so he's not, Nick's work is not new to him. He's very conversant with the area. And in 2022, he's now a full professor and is leading the group on structural physical chemistry. And his work has covered all aspects on nanoscience, self-assembly, and nanomaterial design. Our ICANX challenger is a familiar face to the platform, Dr. Julia Chang. Julia had the great honor of being a PhD student at Iowa State University, where she worked on nanoparticles and non-traditional fabrications of materials, working in organizations and surface modification of different materials. And Julia was a PhD student with Ludovico Cadamatri and myself. And so it's great to see her on the platform. She is now a postdoc with Professor Zhihong Nie at Fudan University. And with that, we're going to jump into the panel. And I asked that our ex-challenger to ask their questions.
Thanks, Martin. And thank you very much for your great talk, Professor Kotov. And as a big fan of yours, here I beg Martin to let me ask 3 questions, if that's possible. Okay, great. Thank you so much. And here's my first question. So, Professor, you showed us a lot of beautiful SEM images during your talk, especially the photon nanostructures. And as we know that noble metals usually have a chiral response greater than organic materials. So my question is there any tryout to transfer these beautiful nanostructures to inorganic materials without destroying its morphology? And what might be the challenges to do so? Please.
Good questions. It's actually very much related to the work that we do right now. I have to start by saying that once we understand how the nanoparticles are assembling, driven by the asymmetry of their interactions, we can start assembling gold particles or silver particles or maybe silica particles. And the same rules apply there. So we used the hybrid system, which has a layer of gold sulfide sheet and amino acid as the example. But if one can make the similar flexible twisted nanosheets from something else, you can do exactly the same thing with inorganic materials. The second part of the answer here to your question is, now when you have, for instance, these particles and chiral spikes and these twisted bow ties, you can start using them as templates. And for example, one of the work that we're reporting in this paper that will be coming out quite soon. I already sent off the valley proofs, and you will see it, I hope, in March, that we coat the bow ties with perovskites. And they form a continuous layer. They retain that shape. And now you have a good example of inorganic material which was templated by these particles. And now you can do it for, say, gold and silica and maybe some other carbon structures. I think that would be a very vast range of studies that will be emerging from it. And Julia, thanks a lot for this question. Absolutely.
Thank you so much. And here's my second one. As you showed in your talk, that graph theory is a very powerful tool. But your example, to me, it's more like it's analysis tool at its current stage. How can we apply it more like a design tool to design the materials that have the exact parameters we need? Maybe we can combine it with a surface treatment of nano blocks or nano wires. Is that something you are considering, Professor?
Again, I'm amazed how good and these questions are. You're absolutely right. It's the analysis in this framework. And the transition into the design needs a little bit more work. And the peaks of that, or some parts of it, you can see in the data for the gels and for the data which are related to the protein particle interactions. So when we describe the gels by using the graph theory, we can see a very clear dependence between, say, the average nodal connectivity or clustering coefficient or some other parameters, and, for instance, the stiffness. And this gives a direct translation into the design space. But you're absolutely right. It's not enough. And what is needed is integration of the physical parameters. For example, say if we are interested in conductivity, how conductive this fiber is. Is it an insulator or it's a metal? And the connectivity and the graph will give you the organization, but you have to have the parameter set that would be in physical space and in this graph space, and integrate them into one design parameter which would be related to chemistry and physics. And after that, you can use the surface modification, for instance, or alloying, say, add more atoms, dope, and change the parameters of these edges and nodes.
Thank you so much.
Yeah, and these steps are still needed to be done.
That sounds very promising. Thank you. And my last question is a general question. That we know that although with a chemistry background, you continue to expand your research interests to other areas, for example, to study the plasmonic nanostructures. So as a primitive researcher, I want to ask you, when you enter a new field, how do you get yourself familiar with the foremost theoretical and research works done in this field, to the extent that you are confident to present your new findings in these areas, Professor?
I'm still struggling with the same question. So I don't think it's it's a question that I know complete answer to, but I can tell you how I did and I do that. So I basically not asking the permission from anybody. So if I want to learn the graph theory, I do it. If I want to enter the catalysis, I do it. If I want to enter the field of batteries, I do it exactly in that way. I understand what the problem is. I formulate this problem in my terms and connect it to the, say, engineering of the materials that we do. And I think in this way you can do exactly the same thing.
Thank you so much.
And I think not being afraid of that is a big part. So yeah, it's hard. And I actually have to tell you that the pandemic was really helpful in that respect because I had some time and I spent time, in this office. I'm now at home. I read a lot of books and it was fun.
Mm-hmm.
And that's how a lot of these new applications of the graph theory in the for the description of the nanometer scale structures came about.
Thank you so much. That's so inspiring.
Nikki, if I can chime in a little bit, actually, it's in the same philosophy that we've been trying to challenge the young scientists, because you see the way science has been packaged by institutions, it is actually captured very well in what Einstein said. He said that my education interferes with my learning. We go through school, which is education, and then we get siloed in disciplines. But then when you look at a young kid, you can teach natural laws to a very young child, and they will understand them. You try to re-explain the same concept to somebody who is a graduate student, and some people will struggle. What is the problem? The problem is not that the mind has changed. The software is still the same. The hardware is still the same. They have the same brain. It works exactly the same. But the environment they have gone through has taught them to work things linearly. And because of being dependent on linear concepts, we then get biased to think in a very linear, additive, step one leads to step two. But to be successful, like what Nick is saying, you don't seek permission from anybody to move from a linear regime to an exponential regime. You almost have to retool as a scientist. You have to retool your brain to say, I can understand philosophy if I want to. Education has helped me figure out that I do have a capability to understand. But it doesn't mean that when I was born a material scientist, I was born a physicist, I was born a chemist. No. You're born with a talent, and that talent can be applied anywhere. And therefore, all you need to do is take whatever the experts are describing in their field and apply your own way of thinking. And this, I think we've addressed this in a different forum where we talked about cognitive diversity. You need to bring your own interpretation of that field, irrespective of what the experts say. Remember, experts, I don't know who say this, but experts can tell you what will not work. They will never tell you what will work. They know how to find the problem. They don't know how to find solutions. Solutions are normally found by people on the fringes. And even if you look at the economic development, a lot of the innovations are not done by the big companies. They're done by small companies. people who are not experts in that field. And so, Julia, and for all the young scientists watching out there, I would like to challenge you: pick up a book. If you see a problem, don't look for anybody to give you permission or to approve you. Pick it, challenge it, and write it your way, not what somebody else is telling you to do it. Thank you.
Oh, well. Thanks.
Does that help you answer your question?
Yeah, it's very helpful. Thanks a lot.
All right, and that's why we have these forums. That's why we need to open these discussions. All right, next we go to our friend in South Africa, Dixon.
Thank you, Martin, and thank you, Nicholas. Quite an impressive talk. I'll be general speaking from the funder's perspective because I know your talk has been very, very specific, focusing on nanomaterials. I'd like to know your partnership with the industry, because you're producing very, very nice nanomaterials of different structures. I've seen bow ties. Where in industry are these materials going to be applied?
Very good question. I work with a number of small companies, and I started a number of small companies. And my impression about this translational path is that if not you, who will? So I am making these steps by myself, and I have very good teams in each company. I have now 3 companies in place, startups, some working on batteries, some on the bow ties. And I work with government and companies. And one of the maybe the path which I would recommend is build a team for the task. We're thinking about the translation as a scientific or technological process, but actually it's very much related to who is in your startup. And I think that the initial choices which are related to who will be your partners, who will help you to translate and to explain to big industry why the bow ties are important, are very essential for this success. I had a number of companies in the past, and some of them failed, and some were quite successful. And eventually, it's very clear to me that in order to get through these initial stages, and in order to see your science being implemented in the products, is related to how you operate in the people space. Of course, sometimes it happens without your will at all. I mean, if we look at, say, the aramid fibers or graphene oxide, it just happened. I mean, people read the literature, and now I hear a lot of kind of stories that it's used there, it's used here, and people asking if I get any royalties. No, I don't, but that's totally all right, because that's how maybe luck sometimes works, that you write a paper and people see how nice it is, but in many cases it doesn't, and you have to do your part in it and show that, say, these bow ties can solve a problem. And I think identifying this painful problem that are encountered by, say, the manufacturers of cars, or the robots at home, or or other implementations, I think that's your homework to be done.
Thank you. That's well answered, and I'm very, very delighted that you are translating your research into specific products. The second question would be, we are looking at collaborations. I'm keen to maybe ask you if there are any collaborations with you throughout the continent, or you only work from your lab?
Oh, I love the collaboration because of the people aspect and because I learn. We collaborate, we as the lab collaborate with, I think you can find the papers from almost all the continents that we co-wrote. And I really like collaboration because of the complementarity of expertise and a different vision that people bring to the problem. As Martin had mentioned, I mean, the diversity in cognition, in perception, what the problem is, I think that's what I value very much. And I think some of the best papers that I have cited here are all done in collaboration. And yes, you need to have your own identity, but and your own scope and your own efficiency, but also the collaboration is a gift. And if people are happy in your collaboration, in your team, I think that's eventually what or how the success looks like and feels like. And as you can see, the papers are representation of that.
Thank you. As a material scientist, the main challenge I face is reproducibility. And if you are to go to large scale, do you envision reproducibility in your, let's say, your nanostructures?
Yeah, good question again. We faced it in the small, in the startups as well. So yeah, I'm kind of very conscious about it. And one of the good things about this dispersity questions is that eventually the variability of the particles do not have tremendous impact on the variability of supraparticles. So, and that's a very advantageous aspect of these assemblies. Electrostatic repulsion can be tuned quite nicely. And since electrostatic repulsion and other restrictions are kind of playing together and making these complex structures, we have a very nice tool to adjust the structure, not risking reproducibility, because this is a thermodynamic effect, and it can be reproduced in liter or in milliliter or in 100 liters.
Thank you. Back to you, Martin.
All right, Nick, thank you very much. I think I'm going to steal one quote from you, and I might rephrase it again. Collaboration is a gift. So thank you very much for saying that. Because in essence, you know, whenever somebody agrees to open their mind for you, that's the only gateway you have to run how they think. But it's one of the most protected treasures that we have in science, people's minds, people's style of thinking, and so it's truly a gift to be able to have collaborations. And so I'm going to hand over to our next panelist, Takuya Nakashima. Please take it away.
Thank you, Matti. So Nick, yeah, great talk as always, and I like your tie.
Thank you.
So actually, we acknowledge your tremendous effort in this field. So owing to your effort, we witnessed the great progress in this field. Actually, in my opinion, so you brought the two big innovations, including the introduction of graph theory analysis to the self-assembling structure of nanoparticle, and the another one is the concept of self-limited assembly. So actually, my first question is about the self-limited assembly. So yeah, actually, we understood that was very, very powerful, the tool to get the micrometer scale complex structures. So now you utilize the electrostatic interactions restriction to terminate the self-assembly. So could you control the termination of self-assembly if you want to go step forward the next level of hierarchy? Maybe another force will be needed.
Yeah, good points. So looking at, say, how we build up, right? So our materials. We start with the molecules. They have certain chirality. It restricts, say, into helices. Then the helices will be assembled at a higher scale. Repulsion starts working, and then into the higher scale. My vision of that, how to go through these scales and eventually get a complex structure, say at centimeter scale or at millimeter scale, that piece of knowledge, which kind of maybe rushed off as maybe something obvious or something a little bit of overlap with human sciences. Complexity is a competition. If you have the competitive restrictions, you will have the complexity. And maybe it's simple. And in chemical terms, it will be a competition of forces. So repulsion plus attraction plus elasticity. And when we want to go to the higher level, we want to keep that competition. So what it could be. The mechanical forces will be a big part of it. So I also start thinking about topological restrictions. So once you have that tool of graph theory, then it has to be connected in a particular way. But that particular ways can be restricted by physics and by chemistry. And mechanics plus topological restrictions is the path up.
I see. Then maybe chirality is a part of topological restriction.
You're absolutely correct. It's a big advantage of chirality, because the reason why we're chiral is because the chirality goes through up into the higher levels. And at every level, it emerges as a structure defining factor, but in a different forms. Yeah, for say the assembly of the helices of DNA, this will be the restricting factor. So it can be only in that way, not in the other way. It has to be L to L and L to D. If we go to the nanometer scale level, we see that the collagen is always have one helicity, and that helicity defines the elasticity of skin and other materials. If we go to, say, the chirality of or at microscale, say plants, it is the easiest case. Why they are helical? That's because the fibers there are helical. That's because they form the bundles that are helical, and that translates in that. So I think that's the big kind of structural foundation, or mathematical, if you want, foundation of chirality as a unifying rule for the building up of complex matter.
Okay, thank you. So my second question is about the self-limited assembly. So you changed a lot of parameters, but the building units are quite simple. Just metal ions and the small organic ligand. So meanwhile, when I was in your laboratory 14 years ago, I saw a lot of layer by layer machine, automated layer by layer machine are working. So accordingly, I came up with the idea of automation of the self-limited assembly. So I'd like to have your comments on this point.
Yeah, Takuya, thank you. I hope that you had good memories about that time. It was certainly a pleasure to know that you remember it well. We now changed a little bit, as you could see. I mean, self-limited assembly started with LBL, absolutely, and it basically led me to ask the question: okay, so we can do it in the surface. The physics is simple. So the particles are repulsing and attracting, and after a certain time, it basically starts only repulsing. It's filled, if you want. So can we reproduce that in the bulk? And that's when the superparticles came. And the next question was, okay, so we can make the supraparticles, but now let's make more fun and change the structure of the building blocks. And maybe they will form longer particles or different particles. And indeed, it was the case. So I see a big positive aspect that the building blocks are simple. But what is true again and again and again, what really matters is the pattern. So, and this is the biological and biomimetic aspect of this story, that in biology, it's not the crystallinity, it's not that order that is driver of the functionalities, or is not the order that makes the diversity and complexity. It's that patterns which can be sometimes not exact. And we need to identify this pattern and say the nacre, it's the pattern, right? And we can reproduce it now from clays or graphene oxide or hydro or other platelets or molybdenum sulfide, vaccines, and others. So once you learn that pattern, you learn the magic basically. But the pattern can be not obvious. In case of nacre, it was luck. It was very obvious. Organic and organic, organic and organic. But there are many other patterns. And what we need to know is how to extract these patterns. And I think that's where the connection between the restricted assembly, why these patterns emerge, how we can reproduce it, is actually coming to life. So why the fibers in the cartilage form that pattern, not this pattern, is because they have certain flexibilities, certain arranging, certain connectivity. And that's how the aramid nanofibers came. So by kind of extracting the math of the pattern, and math is, patterns are mathematical. They're nothing specifically physics or chemistry there.
Okay.
So I'm not sure if it is a long answer to a short question.
So actually the answer was beyond my expectation. So I just wanted to ask so you showed the 81 SEM pictures. So it means the one of your postdoc or the researcher tested 81 conditions with his hand. So, but I wanted to say it can be automated.
Oh my God! Yes, I answered the wrong question.
No.
Yes, okay. I mean, you're absolutely right. It can be automated and should be automated. Yeah.
So you can change the kind of metal ions and also the type of ligands.
Yeah. And now there are some more work in this area which we do, and you are absolutely right. You just change a little bit, and the structure suddenly change dramatically. And that's because you remove one of the competitions or change it just slightly.
Thank you.
Yeah, but you're absolutely right. Yeah. Okay. If I would have an SEM and a robot, if some, Bill Gates or whoever would come to me and say, "Hey, Nick, I have an idea. Why don't you make a robot?" I will. It's a good idea.
Okay, thank you. Yeah, I'm done.
Okay, thank you very much, Nick. This is very, very interesting, and one of the things that is emerging very clearly and tying into the questions, especially what Julia was asking, is how you're able to move from biology to physics to chemistry to math to engineering and tie them together. So I have a question for you that will help people who cannot span such a breadth of complexity, so to speak. Can we use graph theory to abstract or to map out or create correlations with thermodynamic variables? And the reason I ask, thermodynamics is binary. It tells us whether something will happen or not. And in this generation, if you can teach students and young scientists a yes or no answer, it's very easy for somebody to see how it can apply. So parameters coming out of it to pull out thermodynamics parameters or to predict thermodynamic parameters.
My tendency here would be to be cautious. because thermodynamic parameters have a lot of electronic interactions and quantum effects, and of course, I mean, a lot of particle interactions. I will answer it in this way, maybe. We now, in collaboration with André de Moura from Brazil and Paul Bogdan from University of Southern California, we're working on an application of graph theory to structure of phases. Say there is a thermodynamic diagram, and there are many structures there. And it turns out that some phases are very complex. And of course, I mean, some phases are simple. You have balls that form hexagonal structure or some other structures, but some phases are very difficult. And as the particles or surfactants becomes floppier or longer, it becomes more complex. And sometimes the thermodynamics here are very subtle, and you cannot really trace it computationally or experimentally very well. But the structure changes quite a bit. And graph theory, especially the parameter called betweenness centrality, which is long-range parameter, enables us to pinpoint the different phases and pinpoint how this complex system of surfactants and nanoscale structures transition from one into the other. I think about graph theory as Julie mentioned, it's more like an analytical tool at the moment, which helps understanding what's happening there and how, say, this emerges into one complex structure, emerges and transforms into the other. And I think this is quite helpful because it's not messy. We just need to change our mindset from appreciation that some patterns are not obvious, not as simple, and we need to see them through the mathematical combination of numbers. And they change. They're becoming quite obvious if you have a matrix. And that is a very kind of novel. It's a new thing that the graph theory can offer to the very classical field of transition of phases.
Very good. Thank you. Thank you very much for that answer. It's I think as a good talk will do, it leaves more questions than it gives answers. And there's definitely more work to be done to extend the structures, the approaches, and on behalf of the team here, I want to say thank you very much for your talk today. And in continuation, I want to say that you're always welcome to ICANX. And if this was in person, I believe Aris and I would have walked across the stage and presented this certificate to you for being our speaker for volume 131. And but now, please accept our virtual. We'll be emailing this to you. I want to thank everybody for that. I want to also invite everyone to come and join the talk next week to continue this theme on nanotechnology as we listen to Professor Rafaela Busanti, an amazing speaker from EPFL, and she's doing some great work that cross colloidal system to chemistry to catalysis, and excellent speaker. Please join us. And with that, I want to say thank you, everyone, and thank you for your time.
Thank you, Martin, and thanks.
不再是奇迹，不再是幻想的力量。I can， 你也能够像我一样飞越最高山岗。I can， 没有什么可以阻挡心。